Yeah, no, it's not started. I'll start. We've not started. Yeah, I think Abhishek should come. Should we start? I don't know. Okay. Just keep my speak here in case I need. Yeah, okay. So should we start? It's already recording, I don't know. Yeah, okay. So we start. So again, so what we have tried to look at, so maybe we'll, yeah. So what we looked at is this problem. Okay, so what is the problem? That you have a lattice and there are particles. I was asking for two particles, two different kind of particles, but let us do it for one kind of particles at the beginning. So we have a lattice, there are lattice heights I. So this is periodic also. Sorry, periodic. Okay, you have a periodic thing, and each site I has can be occupied by a particle called A, or it can be vacant. I call it 0. Okay. So what does it mean? That A 0 going to 0A means A moves forward with rate P, and A moves backward with rate Q. So you have many particles. I don't know how many particles, and this dynamics is conserved, right? I mean, because the number of particles is conserved in this system. Okay. So then what we want to write, that for A, we write a matrix A, and O, we write a matrix O. So general, the probability in the steady state, we are just saying that P equal to trace of, this is the answers, this is the matrix product answers, right? 0A cross 0A cross 0A, that's the matrix product answers we write. And once we write that, what we need is this, what we need is that MP equal to 0. I think I need a red chalk, I lost it somewhere. Yeah, okay. So what we need is just MP equal to 0, which means that dP by dt equal to 0. That's the equation which you need to solve to know what is the steady state. How many configurations are here? 2 to the power L. Okay, so starting from everything that, no, it's conserved. How many configurations are there? So if the total number of particles is Na, how many configurations are here? The side number of sides are L. C, L choose N, okay? L choose N, that is Na, that is the number of particles, okay? I call it N. So these are the number of configurations, the number of particles, number of configurations in the system. And then, when the particles moves, the configuration of the system changes. All you want is that how often you visit a particular configurations among the 2 to the power L configurations. And the fraction of times you visit a particular configuration is the probability, right? I mean, that's what you are looking for. And that probability is in equilibrium, given a Hamiltonian if you are writing a dynamics, and the probability you already know. That is e to the power minus beta energy of that configuration. And it's a non-equilibrium problem which you do not know what is the probability. The dynamics is given, we're trying to figure out what is the probability. That's the task. And this one, through matrix product answers, whatever with the cancellation scheme, using additional matrices tildes, we find that for two sides, because the dynamics always acts on two sides. Because if you want to move a particle from here to here, you need to know that there is a particle here, and you also need to know that that one is vacant, right? So that is the reason you have to look at what will happen. So for example, if somewhere there is a 0, 0, then nothing happens, right? It is just remaining like that. That's the reason it is 0. Similarly, where there is a site where there is a AA, nothing happens, right? But wherever this one, 0A, if you have a site 0A somewhere in the lattice, this is 0A, so 0A will be lost because 0A will be lost with rate Q, and 0A can be gained from A0 with rate P. So this is possible that 0A will go to, using 0A, it can go to A0 with rate Q, and this 0A also can come from A0 with rate P. Right? No, I mean, that is the rules I have. No, if you allow it to 0, 0, that's a different problem, another day. So today they will not go, okay? So that is my problem, and that is what I want to solve, and that's the matrix. This matrix represents what happens locally. And this matrix, I call it K, and K, so if you want this to be 0, which means that this K operating on first 2 plus K operating on this 2 plus K operating on the other 2 has to be 0, right? And then I say that you can do if you write K operating on this equal to tilde minus tilde, because in the ring, this will automatically make it 0. I still do not know what is a tilde. this is where we left. So, and this equation K, which is 4 by 4 matrix, this matrix multiplied by 0A, 0A, which means that multiplied by 0, 0, OO, OA, AO, and AA. Multiplying by that will give you OO, like O tilde O minus OO tilde. This time, this O tilde O tilde. Similarly, O tilde A, O A tilde. This equal to that. So this matrix operating on this will give you this. I'll finish it. AO minus AO A tilde O tilde, and AA minus AA tilde and tilde. So what is how do you multiply? So this multiply. If you multiply this, left hand side you get 0. So your first equation is this equal to 0. And that is O commutes with O tilde. The last equation is, if you multiply this with that, you get the last column. The last column is A tilde, A tilde. So left hand side you get 0. So this will be A commutes with A tilde. So that is what we did, right? Is it clear at this stage? Yes.
I'm slightly confused. So we have this LCN number of different configurations in our system, right?
Yes.
But we have 2 to the power L states here in the P vector.
Yes.
So now when we say that we have LCN number of different configurations, does that mean that these many number of states have different ways?
Yes. No, we are not. So how to right now? Yes, right now. Let at this stage the number of particles we have not bothered about it yet. Any configuration this has to be true. We do not know how to fix the number of configuration yet. That we will see how to fix it.
For the time being, we are considering 2 to the power L number of.
We are talking of only one configuration, any configuration. Whether those configurations are part of your system or not, we don't know, right? We will fix it some way. We will put this constraint some way that if we want the system to have exactly that many configurations, we will use it somewhere. Sum of configurations is partition function. There you have to take care of it, not now. If I call A as D and 0 as E, would you be happy? Other people will not be probably, because this is much simpler, because you are just directly writing a whatever called A particle as a matrix, because that's a secondary step. I don't know what the question and how to help. Right? I mean, no, I don't know. You want me to change it to DE? Because I will introduce another matrix, so I don't know how to use it. So yeah. I don't know, sorry.
This is basically from taking to -1 to +1 notation to 0 to 1.
No, notation you can use what is, you can call it S and M. I don't care. I mean, the equation remains same, but question is that when you are representing a particle called A, it's better to call the matrix, corresponding matrix A. If it is particle is 0, I could have called it E, but I'm calling it O. It just, you don't have to, then you don't have to remind when I write these equations, matrix, these are matrix form, you don't, you have a confusion what I'm talking about. It's much easier, simpler. Okay. Notation of matrices doesn't, changing notation of matrices doesn't change the algebra. I mean, okay. Yeah, I forgot what I was saying. So wherever sorry. Yeah. So A commutes with A tilde, O commutes with O tilde, and these are the two equations, right? So what are the solutions? Anybody has tried? Yesterday we wrote these equations. Anybody has tried a solution? Okay. So let us try. So what are the type of trials you should do? Like, and first you fix A tilde and O tilde, the tilde auxiliary matrices, because those are irrelevant. It's your choice. You can choose anything. So what are the choices you do? So that's generally, I'm just saying that if you're trying a prescription, like, so you can say that if A tilde equal to zeros, tildes are zeros. This is one solution. Tildes are constants, and tildes are same thing as a constant time A, if it is A tilde. Those are the trials, simple trials. Or a tilde can be something like A1, A2. It's like a projector, some vector out of product, right? I mean, you don't know, but these are the trials, general trials you can try. So simplify if it simplifies. Any of them works is fine with you. If it doesn't, you have to think of more, how to choose tildes. Okay, so if you do this one actually tells you that a matrix which is out of product, right? So that will be A tilde to the power k equal to some constant to the power k. I actually can write that constant. So that is A2, A1 whole to the power k into A tilde. This is simpler equations you get, right? Because if you multiply this, A times A, then you get another A1 here, that becomes a scalar. And then A1 and, let us write it, another one, A1 and A2. Then what will happen is this becomes A2, A1 is a constant, and A1, A2 is your matrix A initially. So if you multiply many times, this is the way. So this is one simpler way to look at matrix algebra. Okay, so these are the tricks when you are looking for solutions. Huh? K minus 1, thank you. Okay? Okay, so this is a general thing, and what we try is this, let us try some of them. So let us take it A tilde equal to 0. So the choice, A tilde equal to 0, and it can be any constant, but 0 also works. So, and O tilde equal to some omega. Okay? Can you now, so these equations are satisfied, right? Because for any constant they satisfy. O tilde is the constant, that commutations, these are satisfied. I don't have to bother about that. This is choice. If it doesn't work, I mean, we have other things also. I'm using some A tilde equal to 0, other one O tilde equal to constant, something. Right? I mean, if you look at them, I have looked at them for some time. If you look at them for some time, you can figure it out. Okay? So A tilde equal to 0. So can you write the equations now? So minus QOA plus PAO, okay, equal to omega A. Omega A, that's the equation. So I will write it the other way, PAO minus QAO. So let me write it again. So PAO minus QOA equal to omega A. Do you get anything extra from the other equation? The minus sign is also taken care of, so this is already satisfying. So you just have one equation, AO minus QOA equal to omega A. So if you find matrices which satisfy these equations, then you are done for this problem, right? So let us say that for time being, let us say that, now you can have choices, again, A, B, you try, right? So try with, first thing is that, let us say A and O, they are scalars. Will it satisfy? Can you satisfy them with scalars? So then it will be PAO minus, so this will be A is a scalar, so I call it A is just a scalar called A, this is a scalar called phi. I mean, these are scalars. So then you immediately get P times P minus Q, because the scalar down they will commute. This is the solution, this is one solution. I mean, this is not a general solution probably, and if you find it for any PQ, then it is a general solution, right? Because you don't have any other parameter in the problem. So P minus Q times A phi equal to omega A phi. And omega, what is omega? It's tilde. That's your choice. You can make whatever omega you want, right? So all you do is that now phi cancels out. No phi there, omega A, sorry. A cancels out. So then omega equal to P minus, omega has a solution, P minus Q by A. Okay, P minus Q, sorry, omega equal to A cancels out, P minus Q times phi. Yeah. So omega has a solution. It can be 0, yes. Numbers, 7, 25, those are scalars. A can be, yeah, matrices are, a scalar is a matrix, one by one matrix. Is it incorrect? Yes, okay. So P minus Q into phi, omega equal to P minus Q into phi. Okay, so then this choice is also okay. So if you say that omega equal to this, then this solution works. So which means that A equal to a constant, A, O is another constant called phi. That's all. This is solution. Right? So now, and A equal to this basically means that the whole problem, the matrices commute, right? So what is the weight of a given configurations, any configurations? It is just A to the power number of A's. I call it N. So probability of any configurations which has N number of A's will be just A to the power, not probability, it's just weight, because you have a normalization constant, A to the power N and phi to the power L minus N, right? Because doesn't matter where you put your A's, they're commuting. So you just count how many A's are there. Are you getting the point? So if you have a configurations A, 0, 0, A, 0, is same thing as A, 0, A, because you know if you get A from here, 3 A's and 3 zeros. So this will be A cube, phi cube. And this is where this will be A cube, phi cube, because these are constants. So in this problem, although it's a non-equilibrium problem, we can figure out what is current in this problem. But this problem has an exact solution now, that if you have, doesn't matter how many particles on a ring, yes? Yes. Are fixed. Also, we want to find out A and O. All of them we need to figure out, because this is an answers I write, right? I mean, when you write this, initially, you don't have tildes. Initially, you are only supposed to figure out only what is O and what is A, then you know the steady state, right? This is getting a solution. A tilde is something which you assume in between as auxiliaries, and once I put it, I have only one equation to satisfy. This AO minus QA equal to omega, that's the only equation I need to satisfy. Any matrix A and O which satisfy this will work. I'm saying that if you take A equal to some identity, A equal to, if you want matrices, and O equal to some phi times identity, it can be I2, I3, whatever. It is scalars, basically they are scalars. Scalars work. Scalar solution works. So the problem has a steady state, it's a scalar. So all configurations in this problem are equally likely. So we have a ring, and some number of A can be called it 1 or particles. Some particles are there, and particles going left and right in the ring. Okay. So the all configurations in these problems are equally likely. That's the statement. Okay. So now can you do, question is that how many configurations are there? So you have to find out the partition function for this. So the partition function, so sum of the weights, because you know that this is A to the power N, phi to the power L minus N, that is true, but there is a normalization constant here. Yeah, okay, so let us keep it here, and let us see in the matrix product answer, how do you do this, how to deal with the conservation, okay. So what you do is the partition function, you have written it earlier, Z equal to A plus O to the power N, to the power L, trace of that. This will generate all configuration, A, all configurations are here, right? This is what you have written it earlier. What we do is that we put a Z here, okay? I just put a Z here for the timing. So this will be a function of Z, right? Then let us look at, this can be written at summation over N, Z to the power N, whatever the coefficient Qn. I mean, if you are not accustomed with method, this is, yeah, I can tell you more. How many people knows what is a fugacity or a generating function? Yeah, okay. So that is the way to count how many A's are there in the system. So basically, all you are doing is that, so there is a configuration, so let us say A like this, and O like this. So how many A's are there? 1, 2, 3, 4, 5. But instead of A, I am writing ZA. So this one will bring me Z to the power 5. A configuration which has 5 A's will 1, 2, 3, 4, 5 will give me a coefficient, because wherever there is a now it will be ZA, right? So this will be Z to the power 5 times this. So any other configuration which is A0, 0, A, 0, right? So for this also it is Z to the power 5. So the coefficient of Z to the power 5 will count how many such configurations are there. So if I write, so that is Z to the power Qn, this is the coefficient. And your actual partition function with n particles will be, sorry, oh, this also wait, okay. So the actual particle, so your Qn of this partition function will be Z to the power n, coefficient of Z to the power n in Z. This Z is the whatever I wrote, right? And how to find the coefficient of Z to the power n of a function? Differentiate. Is there any other way? So this is a function of Z, okay? So there is, this can be written as, how do you write? 1 by n factorial and minus, and dn by dz to the power n, and then you differentiate this with z of z at z equal to 0. This is one way mathematically to figure it out. Another way to figure it out is the Cauchy integral, right? You know this integral, z of z divided by z to the power n plus 1 is a complex integral, and that will figure out, from this will give you the pole, and from that also you can figure out. If you do not know these methods, we will not discuss this. I mean, yeah, it will be binomial expansion for this problem because they are scalars. If it is matrices and they non-commute, then it's a tough problem. You have to figure it out what it is. So for this problem, it is very simple, right? Because this is just ZA. So let us write this for this particular problem. This is ZA small a plus phi whole to the power L summation over, no, Z to the power L. This is the one. And trace will not work anymore. So your partition function is just ZA plus phi whole to the power L, right? So this can be written as CLN Z to the power N ZA whole to the power N and phi to the power L minus N, right? So you can see the coefficient of Z to the power N is Qn. So Qn, if you have n particles, exactly n particles, this is your configuration is CLN and A to the power N, phi to the power L minus N. Oh, summation over n is there. Okay, summation over n equal to 0 to L. But you want only the coefficient of Z to the power n in this series, and that is this, right? So now if all configurations are equally likely, and each of them is A to the power n, phi to the power L minus n, if there are n particles, the partition function is the sum of all configurations with this weight. And that is, if you want to write it, partition function. So in this case, if you write Qn, because all of them same weight, so this will be exactly C to CLN A to the power n, phi to the power L minus n, right? So this is the way you can do it. It is okay? So in this problem, it's a very simple one, and you have all configurations equally likely. Now if you want to find current, right? What is current in the problem? Okay, there is another way to calculate this in the grand canonical ensemble, if you know how to do this. So if you introduce Z, you can actually work in this ensemble by saying that in this ensemble the number of particles, because it's to the power L, this I will do. You know how to do it? If you introduce Z as a fugacity or a chemical potential and try to figure out a particle by fixing the chemical potential, if you know, it is okay. If you don't know, you can figure out from this CLN. Okay. For the simple problems, we don't want to. I will not do this. Okay. So what do you? Tutorial, if you ask me again, I will do it. Not now. Okay. So So there is here you figure it out. And what is the one? What is the? I think I'll do it. Not that. Okay, so there is a Z, which is ZA plus phi whole to the power L. This is what is your partition function is, right? And this has all the thing. So now, so this is same thing as summation over n equal to 0 to L Z to the power n and Qn. So now, if you consider this as your probability or a partition function, then you want to calculate what is n average, because now there are all configurations. You just take all configurations, but with a proper weight. That's what you are doing, right? So if you want to find out n average, so that will be n from here. You want a n here because your probability z to the power n Qn divided by capital Z, right? So your probability of having n particles is z to the power n divided by z to the power n Qn divided by capital Z. That's your probability. So if you want n average, that will be n times Pn summation over n. So that will be z to the power n Qn and n summation over n equal to 0 to infinity, 0 to L divided by Z. That's your n average. But how to get this? This one, n z to the power n Qn, so n z to the small z to the power n Qn summation over n equal to 0 to infinity equal to z d by dz of capital Z. Is it correct? Because your Z, capital Z, equal to summation over n z to the power n Qn. If you differentiate d by dz, then you get n z to the power n minus 1 Qn. And if you multiply by Z, then you multiply by Z here. So this will be n z to the power n z to the power n Qn, and which is here. Okay. So your n average is this divided by partition function. So your n average is always Z d by dz of capital Z divided by capital Z. Okay. So this is same thing as Z d by dz of log of capital Z. Okay. This is the way you can also fix out. So this is n average. So instead of taking n fixed, you can go to an ensemble where n average is fixed. That's the standard trick in statistical mechanics. So you go there and you fix. You just say that n average, you want it to be n, the fixed value, whatever you want, n0 or n, then that will give you a value of Z. And then you can use that Z to figure out any other quantities. That's the way you calculate things. Okay. So now we want to figure out what is the current, and we use this one. So what is n average here? Huh? What is n average here? Your capital, this Z is this. Let us calculate n average. N average is what? Z d by Z of log of Z. What is that? So this equal to Z d by dz of log Z equal to L. One thing is L, and then log of this, derivative of log this, 1 divided by ZA plus phi, and then derivative of this is Z A. Right? So if you want to call density, then n divided by L, So you divide by L. So your density in this situation you know. I don't know which one to erase. This one I can erase now. So in this case you know the density. So density equal to A divided by, this cancels out, ZA divided by ZA plus phi. Okay? Actually, just because you don't have any choice on phi anymore, you can set them to be 1 because they're just a constant. You can take it anything you like. Because for any phi it will work. They are constants, but you can always take it to 1 because normalization will be taken care of by partition function anyway. So you can say that this is, if you put A equal to 1, phi equal to 1, this is Z divided by plus Z. Right? So that is the meaning that Z is called a fugacity, or Z is e to the power minus beta mu or something, if you want a problem. Otherwise, you can directly plot rho as a function of Z. So what is the function of Z? What is rho as a function of Z? So what is Z equal to 0? Rho equal to 0. And Z goes to infinity, rho is 1. So it will start with 0 and it will go to 1. And that is your 1. So which means that every density, particle density, corresponds to a unique Z. So this is the meaning of ensemble equivalence. This is the standard start make I'm repeating here, but for my problem. And this I need because other problem, it is easier to calculate here than going to the canonical ensemble. Studying fixed n, this one, okay? So now we know the relation like this, and now you want to calculate. So A and phi is same, so I will just put 1 plus Z whole to the power L. So your partition function now, Z equal to 1 plus Z whole to the power L. And your density equal to Z divided by 1 plus Z. So these are the two things I know. I want to calculate now current. What is current? Average current, not the current as an operator. So the average current is the number of times particle move forward times the thing when it can go backward, right? So current in this problem can be defined as this, that you have A0, any times we find A0 with probability P or rate P, current has a dimension rate, right? I mean, so dimension is a rate, 1 by time. So basically A0 is the P times A0. So whenever I find A0 with rate P, it will go to 0A. So this is forward move. So the expectation value of A0 is a forward move minus Q times 0A. Anywhere in the configurations, wherever the configuration, if it is 0 and A, this particle can go this way, so it's a left move. So the number of times particle is going rightward on average, minus it is going left, that is the one, is the operator, this 0A average, right? So P A0 minus Q 0A average, right? That is your current. So your current equal to P A0 minus Q 0A average. But then I have an equation here. Kahan gaya? Did I erase it? This equation is exactly that. P A0 minus Q 0A is omega A, right? So this is omega times A. So the current in this problem, so I have to, so the current, average current will be expectation value of P0A. Also here I have written PA0 minus Q0 expectation. So that is same thing as A omega times expectation value of A, right? So now can I calculate omega times expectation value of A? I don't know which one, I can erase this again. I think this one is no more needed. I'll erase this. So your partition function generally, as I said, that this is A plus O. This is I'm generally calculating A plus O to the power L. That is your partition function with a trace. Z is there. Okay. So what is the expectation value of A? A basically means that you just put A somewhere and calculate it again, right? So let us calculate again. So the current expectation value, I will also erase this. But do you remember what was omega that I need? Omega is P minus Q into phi. But phi I am setting it 1. So this P minus, omega is P minus Q. Okay. So now I want to calculate current, and let me see what is the current in this problem. This one also goes away. I need some space. This one also goes. Okay. So what I want is current is trace of first two sides. You have to have 0, 1 or 1, 0, right? I mean, two things you have to put. So basically it is P A 0 minus Q 0 A. So this is two sides are gone. I mean, this is 0 because there are two sides A and 0, 0 and A. The two sides are gone, and then there is T to the power. So T to the power L minus 2 divided by trace of T to the power L minus T to the power L. That is your expectation value. Okay? Huh? So now what we do is that J equal to this. So I'll erase that again. I don't need it anymore. So now this is A. So this is equal to trace of A T to the power L minus 2 divided by trace of T to the power L. But then T, what is T? T equal to ZA plus O. And A and O both have set it 1. So T equal to just in this case 1 plus Z. This is a scalar, right? Are you getting this? Are you with me? Okay. So then this is T to the power L. So this is a scalar. So the trace things doesn't matter. So let us write it. A is just 1 because in this scalar representation it is 1 I am putting it. So this is 1 by 1 plus Z whole square. 1 by 1 plus Z whole square. Acha, there is one mistake which I did. Why? What is the mistake? Yeah, here it should be written as ZA because 1A you are taking out, right? It will also carry with Z along with it. So there is a Z. Z by 1 plus Z whole square. Right? And then omega is also there. So current equal to that, Z omega divided by 1, you are with me. So current equal to, and omega equal to P minus Q. P minus Q times Z by 1 plus Z whole square, I will write 1 by 1 plus Z into Z by 1 plus Z. Right, that is the same thing. And I have a density equation somewhere. What is the density equation? Rho equal to Z by 1 plus Z. What is 1 minus rho? So this is 1 minus Z by 1 plus Z equal to 1 divided by 1 plus Z. Right? So the current in this problem will be P minus Q into rho into 1 minus rho. Now let us see that, okay, wait for here. It's okay? Why this is?
That Z you wrote in the numerator when you are doing the trace over A.
But that probability is, sum has to be 1. Nah? This is a normalization constant. You cannot say, that is the reason I was using weight equal to trace of A, B, whatever, A plus this whole to the power L. That is the probability of a configuration. But you have a normalization constant. If you want to call it probability, you have a normalization constant. That is sum over all of them. Partition function. That is the partition function. Is there any observable one to calculate where partition function is not below? I mean, that is the way you define. So, where? Yes, that's what I put. Yeah, it's put. Here t to the power L minus 2. Yes? This is small z. Let us. Yeah. Average of A, but you are not keeping track of the total number of particles is fixed. So if you have one A, along with you have to put a Z, so that that you have taken care of one particle is, one count you have already taken, n minus 1 particle you have to take. Rest of them has to be n minus 1.
So if it was A squared average, then
Z square. Yes. As many A's you have to put as many Z's, right? Because the count, in the count, if there are total n number of particles, the places where you are putting A's, the 3 particles has gone. Rest of them should have been n minus 3, right? I mean, that Z has to be put here. Otherwise, you are doing mistake. Any other question? No, now let us look at the consequences. Let us look at what is the consequence of this. Okay, so now rho is the density and 1 minus rho is the whole, right? Probability that you have, because it is everything is equally likely, it's like a coin toss, like head is number of head divided by this. So the probability is just rho and 1 minus rho. It's like a lattice which you have n particles. The density is rho, so each point probability of having a particle is rho only, and probability of not having a particle is 1 minus rho, right? So current can flow forward only when there is a particle here, there is no particle here. And the rate is like forward velocity minus backward velocity, P minus Q. So this is like a velocity and this is like this. Okay, current is like this. And if you want to figure out that, yeah. So if you want to find out what is a potential, because next problem we will look for what is a potential. So let us look at this situation when there is a local potential. So this is a different problem I'm talking about, just to identify what is P minus Q in terms of, in a system, you have a current, you have a drive or some such thing. So what you have is that, let us think of a system which is, this is X and there are lattice points whose distances are 1. And you have a potential like that. Okay, so the Hamiltonian is just V equal to something alpha epsilon times X minus epsilon times X. That's your potential. This is the Hamiltonian, this is the potential. And there are particles, let us say there is a particle which was here and this was vacant and particle wants to move from here to here. What is the change of energy? It will go down, or energy will go down or up? And go down, right? And what is the rate? So when particle wants to move forward in this potential, the rate would be what? 1. You can take that to be 1. Okay, if you take that one, then going back, how much energy you gain? There is a particle here, this is the potential. If you go from here to here, what is the change in energy? Epsilon. So it is epsilon, but it is going down. But when you come back, you have epsilon up. So what is the rate? E to the power minus epsilon, or beta epsilon if it is temperature T. So this is backward rate. So forward rate in this case is 1 if the current is in the positive direction. Forward rate is 1. Backward rate is e to the power minus epsilon. That's the forward rate, right? So basically this divided by that, P divided by, if you have a situations like here, AO0A, so this divided by that, P divided by Q equal to e to the power beta epsilon. Sorry, e to the power epsilon. So epsilon equal to log of P by Q. That's your epsilon, okay? In other words, you can say that, in other words, so P by Q, so your equation is P by Q equal to e to the power epsilon. Okay, so now, so that also says that P, if you want to write it in terms of epsilon, P equal to Q e to the power epsilon. So let us write it here. So this equal to, what is current? P minus Q, let us write it in terms of epsilon, and we see that what is the conductance and whatever. So P is Q, and this is e to the, so 1 minus e to the power epsilon times Q is a constant. This is a rate constant, and there is a rho into 1 minus rho. Local detail balance. No, forward I am taking it 1, backward I am taking it minus epsilon. Epsilon only. Normalize minus epsilon, e to the power minus epsilon. Okay. So 1 minus e to the power epsilon, and when epsilon is small, let us say that drive is very small, then we are near the linear. P is Q is e to the power epsilon. Great, very nice. E to the power epsilon minus 1, that's correct. So now if you have small epsilon, like you are what you call linear response regime, right? If epsilon is small, then you can expand this 1 plus epsilon. This you can write 1 plus epsilon, 1 goes. So in the linear zone, Q times epsilon times, so this is approximately, if your drive is very small, then Q epsilon rho into 1 minus rho. That is what you get. So the direction of current is the direction of drive. That is what you get, okay? And of course, if you divide by j by epsilon, dj by d epsilon, rho into 1 minus rho, which is positive. So the conductivity here is rho into 1 minus rho. Okay, so the conductivity in this situation equal to rho into 1 minus rho, and and the current is in the direction of epsilon. So that's what we learn. Okay, and this is a many particle problem, non-equilibrium problem. Current we could get it. Yes. This is size of the system. Yes. In thermodynamic limit, this is true. Otherwise, you have to. So this is, I use that rho equal to z by 1 plus z. I'm using a grand canonical ensemble, which is equivalent to the canonical ensemble with fixed number of particles, only when the system is large. Yes. If you have a question. Huh? Yes, it will. I will try to ask. I'm just saying that this, it's a homework. I'm giving it to you. Next tutorial, you will figure me out, tell me. Because this is a simple particle, right? You tell me that this will be proportional to 1 plus some A divided by L, up to first order in L. If you go to fixed grand canonical ensemble, number of particles, if you fixed, this will come to 1 plus A by L. You want to calculate now? You can calculate it here. So let us say that you want to calculate 1, 0 expectation value in a system where particles are just thrown randomly, L sites. So what is the expectation value of 1, 0? Exactly n particles in L sites. So you just count that, because if all configurations equal light, it's just a counting problem, right? So all you do is that somewhere you put 1 and 0, and the rest, the system size, total is L, you want 1, 0 expectation value. What is that? That is just 1, 0 is there, and rest of the sites, how many particles are there? N minus 1 particles. How many sites? L minus 2. So this equal to C L minus 2 N minus 1 divided by C L N. And divide that this will be rho into 1 minus rho. So this rho minus rho to something, some correction terms, plus something, I don't remember, 1 by L. You just expand, calculate. I think will cancel out. There is no mystery here, 2 minutes. Just write n factorial, n minus 1 factorial, you will get it. So that is the exact result which you have, but this result is same as average density if you put Z. That's the easier way of calculating. In thermodynamic limit, they are same. Still surprised? Are you still worried? Yeah, do the calculations, n factorial, n minus 1 factorial, n factorial multiply. This will n into, this will be n into L minus n divided by L into L minus 1 equal to that, and then n by L equal to rho, and if you take it n, so rho into 1 minus rho into 1 minus 1 by L, so 1 plus, this is 1. So if there is a longer discussion on standard statistical physics which you have not understood, we will do it in the tutorial. Is it okay? Yes. Yes. It is size dependent. If you do in the canonical, it is size dependent. What's wrong? This is the conduct. Yes. This is not Hamiltonian. Driven everywhere. I mean, because this kind of potential is not that, right, it's just like this. It's like everywhere it is, because you cannot support it's a linear potential, you cannot support on a ring. And that creates discontinuity somewhere, and that actually drives the current constantly. Okay, more, I think, yeah, okay. We'll go to the more interesting problems if it is okay with other people, or we can stand here and we can do this also if you want, like, I don't have a problem. I just have, yeah. It's okay? Okay. Yes?
We are computing the expectation of 1, 0 here.
Yes?
It's using this combination.
Yes?
Again, if you try to compute 0, 1, this is also same.
Yes, but P must be there, na? Because the 0, 1 times P. Right. Yeah. Okay. So the current will be minus Q into this factor. Rho into 1 minus rho into a correction term which is L, which is in the thermodynamic limit, this, match with calculation in the grand canonical answer. Any other question here? Okay. So when P equal to Q equal to 0, there is no current because the particle just diffused, right? This is a diffusion. So this is a driven particle in this one. All particles will diffuse in the system. Then it is a sap on a ring, and there is no current at all. And that is equilibrium system. Okay. So when P equal to Q, actually you can show that this is equilibrium system. No current. Okay. So we'll do one more problem. It's the same one, but one more thing. No, I just say that one problem I will do and show you. This is a trivial one because all configurations are equally likely. You don't like it, like, I don't like it, sorry. It's a simple problem, but this is nothing there. Now let us take little more complicated problem and you try to do this. So now you have this equation, but then the lattice side says more particles, one more species. There are A's and there are B's. Okay, so B0 also goes to 0B, and this is alpha, beta, right? So if it's the independent one, anyway, so for this equation which you have gotten is that AO minus O PAO minus QOA equal to omega times A, right? And along with we have also O tilde, those all other equations we have taken it. This is the only equation which you have to bother about. So now with B, you would have the same thing with P replaced by alpha, this equal to beta, and O commute with that, and those equations are anyway satisfy B, everything is fine, right? So B tilde has to be 0. So you have A tilde equal to 0 you have taken, and if you take equal to B tilde, if you do that, then this is fine. A tilde equal to 0 equal to B tilde. And then O tilde equal to omega. As you have taken earlier, it doesn't harm anything, O tilde equal to omega. So then the next equation will be alpha B0, BO minus beta OB equal to omega times B. Okay? So now that can you find solution?
This is not like hardcore system, right? So two of the particles can sit at the same time.
No, there is a hardcore. So let me define the problem. Each site, so now there are, so how many total, right, if you don't have conservations, the total number of configuration is, so you have a lattice, so now let me define the problem. So you have a lattice, there are each site can be either occupied by A or it is B or it is B. And A can move forward, backward with that rate, B can move backward, forward with that rate. When A meets B, it remains like that, it will not change anything, it will not do anything. Okay? Uh-huh. No, they are neighboring sites. So if you have a configurations A, B, nothing happens here, no dynamics happens here. Okay? So, do I have extra equations there? I don't know. So now can you put constants, will it work? Huh? No, let us look at this. What are the equations you get? Somebody has already actually, I will not name it, somebody has calculated it, it seems. So P A0, so P AO, because I'm just saying that A phi, this is phi A, so P minus Q phi A equal to omega A. This is one equation, and alpha minus beta phi B equal to omega B. A, B doesn't matter. So omega has to be this, has to be that. Then phi also doesn't matter. So the scalar solution works when P minus Q equal to alpha minus beta. Okay? Huh?
In general, we call the above phi A and below phi B, then we can construct a general solution O equal to phi A, phi B diagonal matrix, and A equal to A0 and B equal to
Yes.
0.
Yeah, there are other solutions. I'm just saying that first choice is that scalar solution. Scalar solution basically would mean that all configurations are equally likely. How many configurations are there? For a given NA number of particles, so let us say that there are NA number of A particles, NB number of B particles, and the lattice size is L. How many configurations are there? All configurations are equally likely, right? If it is a scalar solution. And at what condition you have a scalar solution? P minus Q equal to alpha minus beta, right? So the difference of rate has to be same as the difference of these rates, right? And that is the cases when you have a equal, all configurations are equally likely. This is simplest one. So how many configurations are there? LC, L, and you choose Na, and then choose L minus Na and Na and B. From that you choose NB. Okay, so that is the number of configurations you can, and then probability of each configuration is of course 1 by that, and that is the reason why the partition function goes down, and you can calculate, right? I mean, this is a simple program, and I don't want to go further. Right, you can calculate the current here also. It's all configurations are equally likely. But as you are suggesting, are there other solutions? Can you figure out some other solutions? Just to tell you that so far, I have not found a non-trivial solution to this problem, okay? Except for the case, I'm just trying to mention, that let us say there is exactly one A and one B. In this problem, just one A and one B. So what is the partition? If there is a matrix, let us say there is a matrix which exists. So what will be the partition function in this case? Can you write in terms of, there are matrices, think that there are matrices exists, and one A, one B. Then within the trace, you can always start it with A, whatever, right now, because the trace is, you can, trace of A, B, C, D equal to D, like, you can start with A. So your partition function in this case, Z, will be trace of, and you don't have to bother about density, particles, this, nothing, just two particles, right? So you start with A, and then B will be somewhere, right? So the distance from B, A, and then whatever, there is a distance from B, so that will be T to the power some distance, X. And then there is a B, and then how many T's are left? And T equal to A plus B plus O, right? Is it clear? And then T to the power X, B, and how many T's are there? You tell me this one. L minus X minus 2, okay. But is it correct, or do you need to write something else? X can be anything. So X equal to can be 0, then it is A, B nearby. And what is the maximum one? L minus 2, because two of them are gone. So that's your partition function. If you can find matrices which satisfy this, this will be your partition functions. But this one, because there is a T, in the T there are B's. So those A's will come, na? You want to restrict that also. Are you getting this point? In this condition, let us say T square. There is one A, one B. In the T square, there is a AA, na? So there are extra A's. How are you restricting that A, number of A's are fixed, 1. In this condition, you also need some extra condition, so that, I'm just constructing matrices. If it would have been very nice if I would have gotten a general solution to this problem. I'm not able to do it, I'm telling you. If you find out, try yourself, okay? Are there matrices which satisfy these equations, okay, in general? So what is the difficulty in this problem, particularly in this problem, is there are additional conservation laws. Okay, we'll discuss that. There are many, infinitely many, infinity means L size conservation laws here, which you cannot tackle because you are not allowing A, B to exchange or to generate. So what will happen is that any configurations, let us say A, 0, 0, 0, B, A, and B, B, 0, 0, 0, 0, A, like that. So between two A's, let us say this is, make it a color A, this A, and there is another A, which is this A. Between A, if there are two B's, all through your evolution, between these two A's, exactly there will be two B's. So the number of B's, not only that number of A's are conserved, B's are conserved, the number of B's between two A's are also conserved. So that is a very hard kind of constraint, and I don't know how exactly to take care of it. And so this is little difficult, but you can try. Like, if you find a matrix solution to this problem, it will be very nice. Okay. But if you write it like that, it's still not correct because there are additional A's which will come here. So if you put a condition along with this, A square equal to 0 and B square equal to 0, then any time in this whole thing you expand, let us expand it. There is a here, and this is T is A, what is that? A plus B plus O times, let us say, and there is a B. Right? And then there is a T, I will not multiply, there is a T to the power whatever. So let us say multiply this. Then there will be a term AA. Once you get the weight will be 0. AB will there, but AA part will go away. Right? Because A square I put 0. A is not 0, but A square is 0. If you take such matrices, then this will satisfy. It just makes sure this is the partition function of exactly 1A, 1B if we use this condition. Right? Agree? Okay, so do you know matrices which are non-zero but whose square are 0? Which are that? Let us try 2 dimension. And they have to be different. Can you tell me 2 matrices in 2 dimension whose square is 0? 0, 1, 0, 0. So you write A, that is correct, A equal to 1, 2 and B equal to 2, 1, A transpose. Yeah, because if you take B times B, then it is 2, 1 and 2, 1 and 1, 2 is 0. 1 basically means that this vector. This is the same one we are saying. So the matrix, this one, in terms of matrix, this is 2, 1 element, 2, 1 element. So this element is 1, all other elements are 0. This matrix is 1, 2 elements is 1, all other elements are 0. So A plus B is sigma x. Okay? So A square is 0, B square is 0. So now we have to figure out, looking at these equations, is there O which satisfy that? O we do not know. So let us try this. What is the equation? P times, can you try this? Look at these equations. The first equation is what? These 2 equations, right? P times AO, we'll do it here. These are gone. Okay. So now let us look at here, look at these 2 equations. These are the equations which will satisfy A you know, O you know. So you write A, I mean, you know, either you can do it with this language or you can just matrix multiply. I think matrix multiply is better because AO, so 0, 1, 0, 0 into O, I call it O11, O12, O21, O22. O is a bad notation, A11, no. What do, alpha 11, no, alpha beta is also there. So tell me something, huh? I will keep O only, O1, O1, O21, O22, okay. So this matrix minus QOA. QO matrix is O11, O12, O21, O22 times A. A is 0, 1, 0, 0. Can you multiply this? Multiply for me. So this is P times, what are the elements? So this one till this one is O21, this one with O22, and this one will give you 0, 0. Minus Q times this one with this one will give you 0, this one with this one will give 0, this one with this one is O21, this one with this one O21, huh? O11, O11, O21. Okay. So now this matrix has to be omega times A. So what does it mean? O21 has to be 0. What is this? This is omega times A. A means what? 0, 1, 0, 0. So O21 equal to 0. 2, 1, 2 is also 0. I think this is 1, 2. O11, 1, 2. O21 is 0. This is 0. I mean, because you want to compare this with that, this plus this with this. So which means that O21 is 0. This plus this with this. So O22 is also 0. And only equation is PO22. So you get an equation P. So this implies PO22 minus QO21. Oh, sorry, O11 equal to omega. Right? Because that's this element is 1 here, omega here. So P times O22 minus Q times O11 equal to omega. This is what you get, one equation. Can you write the other equation by symmetry? Because 2 becomes 1 now, 1 becomes 2, right? So basically P ki jagah, P is right alpha. So this will be alpha O11 minus beta O22 equal to also omega. Right? Now solve them. There are 2 equations, 2 variables. you can still solve them, O11 and O12. What is that? No, 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 the 1, 2 becomes 2, 1. The matrix element, right, I mean, when you write B equal to 2, 1, like, you know, A, if you replace 1 by 2, 2 by 1, it becomes B. That's the meaning. So this equation is this, but 1 by 2, 2 by 1, that's the matrix. A multiply, otherwise if you multiply, you are not convinced. This is alpha, this is 1, this is beta, and this is 1. Sorry, this is 0, this is 1. 0, 0, 1, 0 times this minus beta times this. So you convince yourself that this is the equation. Okay? So now the solution. I think yeah. You can solve this now. I mean, you know, that is not very difficult, but so P times Q, if you multiply alpha, so let us say that you multiply here Q11, so you multiply alpha here and Q here. These are linear equations. So if you multiply alpha here, then this is minus alpha Q01, and Q here, then this. So alpha omega plus Q omega, I am multiplying by Q, then these two cancels out, and here I multiply by alpha, so this is equal to alpha P, plus from here I get Q minus beta Q times O22. One, one. Yeah. This is correct as far as I know, but if you think multiplication gives you different ones, try to check. Okay. So then what you get, the point is O21, E is a diagonal matrix, right? And you can figure it out what are the diagonal elements. One element I have figured it out for you. So that is alpha plus Q divided by, so O22 equal to alpha plus Q divided by alpha P minus beta Q. This is O22. Okay? So your matrix O will come out to be alpha, here this one is 0, this one is 0, and here outside you have 1 divided by alpha P minus beta Q. I think I will try to check whatever. Huh? No, 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 you have an equation. O21, from here you get 1, 2. This one is 2, 1. Okay, I trust you. This is 2, 1. So O21 can be anything, I am setting it to 0. It's still okay. I mean, I'm looking for a matrix, right? Okay. No, there is nothing, I mean, there is nothing, that doesn't make me, if you don't have to have the matrix which is unique, right? I mean, you know, you can, any matrix which works, it works. You are saying that the O11, O2, yeah, okay, we will check it after during lunch, we'll multiply the matrices again, right? I mean, x plus y equal to 3, x minus y equal to 7, and solve it again, and we see whether your solutions are different from mine. But okay, so for the time being, that is the one, okay? Omega by alpha P minus beta Q. And this one is Q plus beta. And by symmetry, this has to be P plus alpha. That is your O. Okay? So now we know A, B, and O, so you know the solution of this problem. Okay, so I will be giving you another problem set of like 3 pages. So one of the problem is this. Okay, so this is the problem number 1 in that problem, and all these details are there. Okay, So now can you calculate, so what are the things you can do here? So here we can see that when p plus alpha equal to q plus beta, let us say that p plus alpha equal to q plus beta, which means that p minus q equal to beta minus alpha. Did I wrote it wrong? P plus beta q plus alpha. P plus beta q plus alpha. So that's the matrix. P plus beta, because p and q are the same, a and b, like whatever the role plays with p, the same role play with alpha. So if it is p plus p, yeah, here I have a mistake. So then that will be p minus q. Let me write it again. So p minus, p plus beta q plus alpha na. So p minus q equal to alpha minus beta. So this is the condition, p plus beta q plus alpha. Yeah, that is the condition, p plus beta equal to q plus alpha. So if you put that, if this equal to that, then this also goes out. So this becomes identity. Once this matrix becomes identity, then the problem is similar to the previous problem which we discussed earlier, right? I mean, the one like p minus q equal to alpha plus beta, there is a scalar solutions and things like that. So no, I don't need. All I'm saying is that just a minute ago, I have solved that when there is a scalar solution. And I'm telling you that for the scalar solution, you need the matrices 0 should commute with everything. So this becomes identity. Then the 0 can go anywhere. So then it will make all configurations equally likely. Doesn't matter where A's or B's are. Yes. So that is the one, which means that if you want it to be identity, then this has to be same as that. And that condition is what you have seen earlier. To get the matrices, you don't need it. Is it clear? So I'm saying that the solution is this. I don't need this condition. This condition I'm trying to show that what we have gotten earlier, that all configurations equally likely in this problem, only when p minus q equal to alpha minus beta. That is also, this solution confirms that. That is the result. So now, what are the other things you can?
So what happens physically when alpha p equal to beta q? Because that's when the solutions will.
These solutions will not work. Yeah.
Physically.
I don't know. No, I don't know. These solutions will not work, but are there other solutions that I don't know? Alpha p equal to beta q, it will not work. Yes. I don't know. You have anything? No, just there are two particles. It's going like that. Alpha p, product of this is same as product of that. Then this solution looks like this solution at least would not work. Is there anything which goes wrong? Actually, nothing goes wrong. You can always take omega to be anything, right? This is not the, there is nothing, omega is still sitting there. You can take omega equal to alpha p minus beta q, it's okay. Because omega is still sitting there. Look at these equations, right? So if you look at these equations, why there is in the matrix, when you write the matrix, there is an auxiliary which is sitting there. It appears as if when you have a solution, there is some arbitrary solutions, right? Because the auxiliary has nothing to do with the state, right? So how is it possible that the auxiliary is sitting there? That is because you look at this problem. So if you have a solution, if A is multiplied by a constant, something, omega 3A, it also solves it, If A solves this equation, some A, then 3A will also solve it. Is it clear? Huh?
So when we had these A's and O's in one dimension,
Hmm.
not one by one we had taken this number, then we had also these tildes to be numbers.
Yes.
When we are defining this to be 2 by 2 matrices, I mean A and B,
Here also tildes are numbers.
should not we again write it as omega into I?
Okay. Numbers are numbers into I. Yeah, okay. Okay. So the point is, did you see that? If I find it 7 and a 7 here and a 7 here, A ke saath A times 7, then still satisfy, na? 7, 7 cancels out. B ke jagah 4, 4, 4, that also cancels. So there is arbitrariness there. And that is the reason I could have always chosen omega to be anything. And I will choose it suitably so that, right, so omega, there is nothing wrong happen. There is no physical meaning out of it. I can choose omega to be anything. There is nothing special.
You can observe the denominator.
In the normalization. So I can choose omega to be this. Actually, just because it is like this, what I want rather, I will choose it omega such a way that the matrix becomes P gamma 0, 0, 1. This is easier for me. Okay, I will choose omega accordingly. I don't have a problem with this. What is gamma now? But gamma I cannot choose arbitrarily. What is gamma? So gamma equal to P plus beta divided by Q plus alpha. So when P plus beta equal to Q plus alpha, you have a scalar solution. That is the one when gamma equal to 1 is a scalar solution, which means that this is identity. Okay, omega are chosen accordingly. Omega, what is omega? Q plus alpha, alpha p minus beta q divided by q plus alpha. Huh? So omega, I'm setting it omega equal to, now let me, okay, omega equal to alpha p minus beta q divided by q plus beta. Yeah, I think omega I have chosen here. Q plus alpha? Q alpha written.
In omega, the denominator. Plus alpha.
Okay. So I think okay. So now we will go to, so that problem can be solved for any omega, any alpha, right? We will go to a solution when, make it little interesting. So basically what we do is that let us say that P, which one B diffuses, PQ will keep it like that. Alpha equal to beta equal to psi, that's what we will take. Okay, so what will happen now? So alpha, I will take alpha equal to beta equal to psi. So here, what will be the alpha equal to beta equal to alpha equal to beta equal to psi. So this is the problem where there is a particle B which diffuses in the system, and there is a particle A which drifts because P is different from Q. Log P by Q is epsilon. So there is a particle A which is driven, which is generating a current in the problem, but B just diffuses in the lattice. Question that what will happen and what is the current. You can generally find current, what is the current of A, current of B, those you can figure out, but this is a special case, let us consider. You can do what, yeah, I'm just doing one calculation for you. So when alpha equal to beta equal to psi, so what is gamma? Gamma equal to P plus psi divided by Q plus psi, and omega equal to alpha equal to beta. So this is psi, alpha equal to beta psi, P minus Q divided by Q plus psi. Okay, so this is when alpha equal to beta equal to psi. Now let us try to figure out what is current. So what is current in the problem now? Let us the current of B. So the B current is just psi. So it's right. I mean, so your problem is now A0 going to 0A with PQ and B0 going to 0B with psi and psi. These are the rates, right? So what will be the current in this problem? So it looks like can there be a different current for A and B physically? Huh? It is not possible, right? Because they don't exchange, they do nothing. So if A has to move through a circle, B has to move forward in the same rate, right? Same, as many times A makes round, B has to make that round because they don't overtake, right? So the current of A has to be same as the current of B. So here you have the current will be proportional to P minus Q. You can think of well, very nice, P minus Q is something non-zero current. But it looks like B, psi. How is it possible that that is giving a current? So the current, because A is moving, it is generating a current with B, on B, okay? So the current on JB has to be same as JA, but let us calculate JB, because that is most surprising. So what is that? It is psi times B0, so that will be JB equal to psi times B0 minus 0B, okay, times T to the power L minus 2 trace divided by trace of T to the power L, okay. So now 0B, so this is B0 minus 0B, because this is psi into B0 minus 0B is omega times B. I mean alpha equal to beta equal to psi. So B0 minus 0B equal to omega times B. I will also replace this. So this equal to trace of omega times B. So I will put it equal to omega into trace of B T to the power L minus 2, trace of that divided by trace of T to the power L. T to the power L, okay. So can you see that this is exactly T of L minus 1? So this is, I'm saying that this is, if you have the partition function, this is ZL, this is ZL minus 1, okay, omega times that. Why? Because you figure out what is ZL. ZL is this, right? So you could have started with B, T to the power L minus 2A, but then the A is absorbed inside. A can be anything, right? B T to the power L minus 2. I think we are kind of, it's already time. So we will calculate this. We will calculate this next time, next class, okay? So the current can be calculated. I mean, if nothing, the matrices you can multiply, because there are only two matrices. So B equal to 2, 1. B equal to 2, 1, right? So if you put it 2, 1, just here let us put it here, 2, 1. So this is T to the power L minus 2, T1, 2, 1, divided by trace of T to the power L, okay? So we will calculate this next class, okay? Yeah, I think this problem will finish, and then, yeah. And we have this kind of, all these problems, like, I've kept it here, so you can see it.